Well, thank you very much. I'd like to thank Tony and Sangyu for inviting me and for being very kind hosts. So anyway, what I want to do is I want to show you some graphs that have an interesting property and how to attach some symmetric functions to these graphs and then some properties. So symmetric functions is just like a polynomial you attach and it has some special properties. So here I've drawn the graphs with partitions. Do you see? Partitions is basically how many I'm encoding, for example, the partition 3, 2, 1 by this diagram, like a Ferris shape with 3, 2, and 1, right? So this is like 1, this is 2, 3, 2, 1, you know. And I'm ordering them in a poset, partially ordered set by inclusion. So if you can put this diagram, oops, I can put this diagram, fit it into this one by overlapping the corners. So therefore, there's an edge between these two. And so this is a graded poset because everything in each row has the same number of boxes. Okay? And so this is called the partition lattice. And then there's notice that I drew it twice, and this one has arrows going up and this one has arrows going down. So I'm going to call this the up graph and this the down graph. And I'm going to define two operators, up and down. So up takes a vertex and sends it to the sum of everything on top. So u of, for example, this. You want to help me out? It's well, it's this plus that plus that. Okay, and the down operator of this, well, it's this plus that. Okay, now we can combine them. I can apply u and then d and just extend it linearly. So I can do, for example, d of this. So d u, you can think of it as this, of this is just d of the sum of these three. And so d of this, of 3, 1 is 3 plus 2, 1, right? So this is this, right? D of 2, 2 is just 2, 1 because there's only one edge going down. And this one is going to be this plus this. Yeah? And now I can do the same thing. I can apply u here. And I can do ud of this. Okay? And now it's going to be u of this, which is u of this, which is 3 plus 2, 1. Right? This is this. And this one is going to be plus 2, 1 plus 1, 1, 1. Okay? Y'all with me? Yeah? Stop me if anything. And so what if I subtract them? du minus ud applied to this shape. I get this cancel out. This cancel out. And I just get this. And in general, in this partition lattice, we're always going to have du minus ud is the identity. And that's an exercise to prove. It's from the fact that you can always add one more corner than you remove. Okay? So this is a special kind of graphs called Fomin dual graded graphs. Which are based on something called Stanley differential posets. Stanley differential posets is when the posets are the same, and sometimes we're going to have a different graph here and here. Okay, so we have a nice pair of graphs, and now we would like to attach a polynomial to it and see what properties we have or things like that. So let's see. Well, what we're going to do is we're going to attach some labels to these edges. And so the label is going to be the diagonal where I'm adding a new box. So I'm going to call these diagonals like this. This is my 0 diagonal. This is 1. This is 2. 3, 4, so on, minus 1, minus 2. You see what I'm doing? And so, for example, this edge is a 0, right? Is the 0 too small? This edge is a minus 1. This is a 1, 2, a 3, minus 1, 1, minus 2, minus 3, 0, minus 2, 1. You don't see it? Did I miss any? Okay, I'll do it again in here. Here, I'm adding, this shape is here. Okay? And this shape is this. You see it? So I'm adding a 3. Basically, think of this. I'm labeling the diagonals. And so here I'm adding a 3, so I put a 3. Okay? Here I'm adding, well, this one's 0, 1, 2, minus 1. So I'm adding minus 1. So this is minus 1. Here I'm adding a 2. So 2. And I keep going, right? Minus 1. Sorry. Minus 2. Minus 3. So everyone with me? Okay. And now I'm going to attach a polynomial to each one of these partitions. Okay, and those are symmetric functions. How many are familiarized with symmetric functions? Schur functions? Okay, so it's a polynomial attached to each partition, and they're nice. So, okay. Okay, so I'm going to define one thing, which is a quasi-symmetric function. If you've seen Schur functions, this is not the definition you might have seen. But basically, quasi-symmetric functions, they're indexed by composition. So give me any sequence of numbers, small, like, I don't know, of like short. 2, 5, 6, 7, 6. That's all. 2, 5, 6. Okay, let's make it 2, 5, like 1, so you see it. So M251 is basically the sum of all monomials that have chain of exponents 2, 5, and 1. So it's x1 squared, x2 to the 5, x3 to the 1. Okay, and I want this order in the indices. So x1 squared, x2 to the 5, x4 to the 1, and so on. So, you know, x10 squared, x25 to the 5, x99 to the 1, and so on, right?
How many variables are there?
There's infinitely many variables. They belong to the ring of polynomials. Okay, so just a polynomial, and I always want these 3 increasing. So it's not a symmetric function, but it's just it's called monomial quasi-symmetric functions. There's more families, but there are bases. Well, I haven't told you what a quasi-symmetric function is, but anyway, there are bases for the ring of quasi-symmetric functions. Okay, so I'm just going to take, for example, this this partition, I'm going to construct a symmetric function for this partition. So I take all the possible ways to go down to 0. This is, well, to the empty set. And for this partition, there's 3 ways. Yep. So I go, I'm going to draw them here. You see there's 3, right? And the sequence of labels are minus 1, 2, 1, 0. The next one is 2, minus 1, 1, 0. And the next one is 2, 1, minus 1, 0. Y'all with me? So I'm gonna call them minus 1, 2, 1, 0, 2, minus 1, 1, 0, and 2, 1, minus 1, 0. Okay? And now I'm going to look in this one of these chains, where is there an ascent? So an ascent is when I have a small number followed by the bigger number. Okay? And so here I have this one, and here I have this one, and here I have this one. Okay? Because I'm going from minus 1 to 0, minus 1 to 1. Here 1 to 0, that's a descent. This is going lower. So I look at the ascents, okay, and I'm going to create, I'm going to write down the sequence of numbers between each 2 walls. So the first one gives me the composition 1, 3. The second one gives me the composition 2, 2. And the third one gives me the composition 3, 1. Yeah? Because there's 1 and 3 numbers, and there's 2 numbers and 2 numbers, and then there's 3 numbers and 1 number. Okay? And so I go like this. And now I have this thing. So I add the monomial M13, M22, M31. Okay?
Is there always the same amount of ascents?
No.
Okay.
There can be more. These examples are too small. But
there can be different numbers of ascents in the different...
Yeah. I can. Yeah. Pretty sure. If it's not, I'll let you know later, but I'm pretty sure it is. You can. So I add these ones, and then I add like everything that refines this. So like I take each piece and I am allowed to break it. So I also add M121, M112, and M111. And here I'm allowed to add M211, M112, M1111. Here I'm allowed to add...
Isn't M121 equal to M112?
No. 1 second. The question is if M112 equal to M211? No, it's not, because this one has the monomial x1 squared, x2, x3.
Yeah.
And this one doesn't. Because it has to be xa to the 1, xb to the 1, xc to the 2, where a is strictly less than b, strictly less than c. I guess I didn't define this properly. I should have said m of alpha, where alpha is the partition, alpha 1, the composition, is equal to summation of xi1 to the alpha 1 all the way to xik to the alpha k for I1 strictly less than I2 strictly less all the way to ik. Okay? And so I add all these, and magically I get some function associated to this partition. Right? And that function is a Schur function. Okay? Any questions so far? So the Schur functions are very special because they are symmetric, which means you can take your variables and shuffle them around and you still get the same polynomial. Like you still get the same function. Okay? And not only that, but there are bases for the ring of symmetric functions. So let me show you quickly. So lambda is a ring of symmetric functions. Which is basically, think of all the homogeneous polynomials that are invariant under switching the variables around. Okay, so they form a ring, and so the S lambda are a basis for this. And actually, this set where hk is equal to S of a row of length k is a generating set. So you can express a symmetric function as a sum products of these h's and also as sums of s's. Okay? Any questions so far? Okay, so let's see. So now I'm gonna go to like different sets of like different graphs here, and on these different graphs I'm gonna create new sets of symmetric functions that belong to like a different ring and things like that. Okay, and the duality of these two graphs actually translates to the fact that these basis is also a dual basis, in the sense that there's an inner product that makes S mu, like S lambda S mu, equal to the Kronecker delta of lambda mu. Okay? That's exactly the same as saying that these two graphs are dual. So any questions so far before I go to the next object? Okay. So
wait, I have one question.
yes.
So for HK, you define as the S of the one partition.
Yeah.
And so then the next notation is lambda
So-
is a C of.
Yeah, there's actually a better way to define HK. It really is this. Is the sum of all monomials of length k. Okay? So not this. Well, actually, SK is no. Yeah, you can think of, for example, H1 is equal to the sum of x's. Okay? H2 is the sum of all monomials of degree 2. So x1 squared, x2 squared, x1, x2, x1, x3. Okay? You can think of this as M1. You can think of this as M2 plus M11.
So this is because for this partition, every place is a descent.
Yeah, because if I start here at any row, everything is a descent. So I'm really adding M2 plus whatever I can refine it. So the next one is H3. All the monomials of length 3, so x1's cubed plus everything, plus x1 squared x2 plus everything like that, x1 x2 squared, everything in the sort, x1 x2 x3, and everything like that. Okay? And this is the same as M3 plus everything that refines it. So plus M21, M12, M111, where your M3 is this, your M12 is this, 21. Your M12 is this, and your M111 is this. So these functions are clearly symmetric, right? And so another basis for this would be H lambda, where H lambda for a partition like I can take products of H's, and all these products of H's for partitions are going to be a basis for this. Yeah? But that's actually not the prettiest basis. The prettiest basis is the basis of Schur functions. And you can see that these functions are symmetric because I can switch the monomials around and that doesn't matter. See, M112 is not M211 in the same way that M12 is not the same as M21. But in H3 I'm adding them both. So if I flip two variables, I'm still living in the same polynomial. Okay? So these functions are symmetric and these are not. So make sense? Okay. So I'm going to define another object which is similar to a partition, but it's called a k-Schur. Okay, and for a k-Schur, I'm just going to show you an example of what is a hook. So let's say we have a partition. Okay, and for a cell over here, I'm going to define the hook as everything that is basically in this diagram. Okay, so you go as far as you can until you hit the partition, and as down as you can until you hit the partition, and that's the hook. So this hook has length 1, 2, 3, 4, 5, 6, 7 boxes. Okay, so for every box I have what's the hook length, which is the length of this. And so a k-Schur is a partition with no hooks of length k. Okay, so let's try to imagine, for example, what's a 4 hook? What's a 4 core? So is that a 4 core?
No.
No, because there's a 4 hook, right? What about this? That's a 4 core, right? What about this one? Is that a 4 core? So yes, right? Because this hook's length is 1, 2, 3, 5, and 1.
It's not at least k or
Huh?
something. Okay, so it's exactly k.
Yeah, exactly k. So this one is also a 4 core. So let's worry about 3 cores for now. They're more simple. So these are okay. This is not. Let's try to remove all the 3 cores from this graph. Okay? Because now what I want, this is the goal. We have a pair of dual graded graphs on partitions, and now I want a pair of dual graded graphs on k cores, so that I can do a symmetric function for k cores. Because someone once asked the question, hey, is there symmetric functions for k cores? And because they show up in some geometry thing and they're interesting. So let's try. Let's try see what happens. What's a 3 core? So what is not a 3 core in that graph? Well, this was not, right? Because it has this 3 hook. So not this. What else is not a 3 core? Is this a 3 core? Is it okay? This one? It has this one. 1, 2, 3. So I have no good. This one is. This one. It has this 3 hook, right? Yeah. What about this one? That's not a 3 core. Not a 3 core. Not a 3 core. Okay. So I'm gonna say, okay, why don't we do the following? Why don't we just erase all the 3 cores from this drawing and keep the edges, or by keep the edges I mean to say keep the inequalities, like if something is underneath another one, stay there, and hope for the best. Let's see if we have a dual graded graph. So I erase this. I erase this. I erase this and this and the label. I erase this, and I'm going to keep the edges, which kind of would look like this. See how I'm going to turn this one into one edge, and this one into one edge, and this one and this one. So I'm basically doing this. Whoops. So that seems reasonable, right? I took the k cores and I put them organized by containment. So it's also graded. It's not obvious that it's graded, but it's graded. Like there's not going to be like a cycle of like 3 or something like that. Yeah. And let's do the same here. Okay.
So what is the definition of graded?
Yeah, graded really, a graded poset really means you just have a bunch of levels and only edges between these levels.
But isn't every poset like that? Or?
No, because you have this. A poset really means a set where there's an order condition. So right. You can give 2 elements.
Oh yeah, yeah. Okay.
Yeah. So this element can be fixed amount on this, and there may not be a smaller path.
Yeah.
So yeah.
Is graded the same as ranked?
Ranked is the same as graded. Yeah. So maybe ranked is the word I should be using. Okay. Thanks. Okay. So this is ranked. And let's try to do the same thing here. It's finite. Well, not because you can go forever. You can make really big k-cores. They don't have to. They don't get bounded. I'll show you a recipe to make k-cores that you can make them like crazy. Yeah. So I like this and this and this, and what am I doing? Okay, and I did this. Oh, now I go down. So now it's gonna make sense why I used 2 different graphs. Okay, so we're doing this, and we got here, and we're like, okay, we hope that that's a dual graded graph. And so we took an element and said we apply up, and then apply down, and then apply down, and apply up, and try to subtract them and hope that we get the identity, but it doesn't work. So we said, okay, let's try something else. So we raise these 2 edges. And that still didn't work. But we didn't give up. So out of desperation, we multiplied these edges by 2. And now it works. And by this I mean the down operator of this is 2 times this plus 1 times this. And so if you do that, you get a pair of dual graded graphs. Okay? And so, well, now the question is, how do we explain these graphs? And so this is how we explain them. These ones we're going to call the weak order, and this one's we're going to call the strong order. Okay? And the weak order means if you have a k-core, it's underneath another k-core. If this one is obtained by this one by attaching some isolated cells. Okay? So from here to here, you're attaching these two. So there's an up edge. From here to here, you're attaching these two, which are separated, isolated, right? So it's an edge. This edge is not there because I'm attaching two boxes, but they're together. So that doesn't work. And so this is how we define this order. And this order is slightly more complicated. It's actually simpler, but the multiple edges are more complicated. This order, if you forget the multiple edges, this is containment. So there's edges between two cores. If this one is contained here. But how many edges? Well, as many as connected components in the difference. So if from here to here I obtain this one by adding a few things, like 3 things, then I have 3 edges going down. Okay? And so for example, from here to here I'm adding 2 connected components, so I have 2 edges down. From here to here I'm adding only 1 connected component, so I have 1 edge down.
And this one is also the number of copies that you could pack in. But in general, it's not that way.
The number of copies?
I could pack 2 of those guys.
What's pack?
So there's containment, but then I could actually fit that guy and that guy in 2 different ways, right?
Oh, maybe that's true, but maybe not. I mean, that may work here. I'm not sure if it works everywhere, but good observation. That's a good question. So you're saying that I can fit this one here, here, and here, so there's 2. Okay, when I show you the recipe for making cores, it may be clear. I'm inclined to think that it's just a coincidence here, but it may be something. Yeah, it may be true.
It's too small. So
It's hard to tell.
Once it's getting bigger.
Yeah. Okay. Okay. So, and now I can label these things in the same way. I can label them. Okay, this one, let's not worry about the label because it's complicated. I'll show you in a minute. And this label is easy because I'm just going to add, see here I'm adding a -1 and a 2. So I just go -1, 2, right? You see what I'm doing? Adding the diagonals. I'm adding a diagonal called -1 and I'm a diagonal called 2, like before. And then this one I have a 0 and a -1, 1, -2, and I'm adding a diagonal a box at diagonal -2 and a box diagonal 1, so -2, 1. Okay, just like before. This remained the same. And these 2, I'm just gonna pick the toppest box in the component that I'm adding, in the most top right. So this is -1. And this one's 2. It's not really that important. Okay? So I label these things the same way. And I'm not going to worry about this graph, but there's a symmetric function that fits in this graph. And there's a symmetric function that fits in this graph. And they're bases for 2 spaces that are dual. Okay? But I'm just going to show you this one very quickly. And it's basically the same idea. So I can go slightly fast. Let's define the symmetric function associated to this. Okay? So I look at all the possible ways to go down from here. There's 1, there's 2, because I can go on this edge, and there's 3. So I don't need to draw the paths, but you can believe me, or check yourself quickly. You're probably quicker than me. That the number of ways to go from here to here is 2, 1, 0, -1, 1, 0. and 2 minus 1, 0. Yeah? With a sense at nothing, here and here. And so I'm going to be adding the following monomials. M3, M2, M2, 1, and everything that refines it. Okay? There's also power of 2 here. So, and this is going to be my symmetric function S, indexed by this k-Schur, and I'm just going to put I don't remember if I put a 3 or 2, but I think I put a 3. And 3 is because 3 cores. Okay? And these are called k-Schur functions. Okay? And they are very special. They are not a basis for the ring of symmetric functions, but for the following ring. So a subring of the ring of symmetric functions. We call it this. This is called this, and it's contained in the ring of symmetric functions because it has a subset of the generators. Okay?
All symmetric functions of degree k.
No, because you can have HK, that's degree of 2k. It's just a subring. They're also infinite. They're also as degree as high as you want it, but it's just a subring of this. And it's also, you can see that in the same way that I can multiply these ones and obtain a basis on partitions, right? I can also have a basis of partitions like this, right? But since these are all smaller than k, then these are k-bounded partitions. Okay? So it's just a different space, and the reason why we study the space is because they appear in geometry. Like the ring of symmetric functions is the cohomology of the Grassmannian, something I don't even know what it is. Cohomology of the Grassmannian. This homology and cohomology. This is the homology of the affine Grassmannian, and the same. These ones also show up, and so that's kind of why people start worrying about the symmetric functions and these objects. So everything kind of clear with k-Schurs? I'm going to quickly show you like a generalization of this. So it's basically what I want to do now. Sorry that I make you switch around. But what I want to do here is I want to add some more vertices here and make this into a bigger graph and get a bigger family of symmetric functions in something called the affine Nilcoxeter algebra. Okay? So I'm going to show you a recipe to make k-Schurs. That's going to be the basis of and so you can play and we can make like a really large 3-core or something. So I'm going to put I'm going to put the plane like this, and I'm going to label my diagonals 0, like 0, 1, 2, 0, 1, 2, 0, 1, 2, right? You see what I'm doing? Okay, so I'm basically modulo 3, and it would be modulo k, right? And I'm going to start adding boxes, and every time I add a box, I'm going to add all the possible ones of that residue. So I add a 0, okay? And then I can add a 1, for example. Now, if I want to add, for example, a 2, I have to add them all. So I have to put this one, and I have to put this one. I can't just put one of them. And if I want to add, so do you like the 0 or do you like the 1? The 0. So I add a 0. then maybe I add the 1, so I have to add them all. 1, 1, 1. Then maybe I want to add the 0. And if I do this, I'm always going to get a k-Schur. Notice that it's impossible to get this. Because if I started with the 0, and then the 1, and I put a 2, I have to put this 2. Okay? So I'm never going to get a 3 hook. That's kind of cool, right? And so you can imagine playing in this thing and making a humongous k-Schur. Okay?
In last step, do you put 0?
If I do what? If I want to put a 2? Do you want me to put a 2 here?
No, no. In last, you put in 0.
0. I did.
Not 2.
I can put whatever I want as long as I can add it. So here I can add a 2. Well, I can only add a 2. But sometimes I have 2 choices. Or 1. What I cannot do is add a 0 because then I don't get a partition. But so this is a recipe for adding k-Schurs. And that is actually going to help us to make these graphs more general. So I'm going to introduce something called the affine symmetric group. Do you know the symmetric group? Familiarize with the symmetric group. And the generators, right? So I'm going to write the symmetric group. As Sn, okay, is going to be generated by S1, S2, all the way to Sn minus 1, where these are the simple transpositions, right? You've seen this, yeah? Si is equal to I plus 1. So I can write every permutation as a product of these generators in more than one way maybe, or one way, or and these have relations in between them. So the relations is, if I square this generator, I get the same thing. I get like if I did nothing, because if I swap 2 things and swap them back, it's like, well, right? So Si squared equals 1. Si Sj is equal to Sj Si if I r and j are far apart, and the braid relation. Okay, this defines the symmetric group. So I'm going to make the symmetric group larger by adding 1 generator. And my generator is going to be S0. So this is going to be called the affine symmetric group. Oops, symmetric group. And it's going to be Sn, little tilde here. Actually, can I just use a K just to make this the same K as those? K. This is S0, S1, S2, all the way to Sn minus 1. Okay? And I want to say we have all these relations.
You want that to be a K?
Thank you. And I also want S0 is K minus 1, S0 equals Sk minus 1, S0 is K minus 1. Okay, so I'm wrapping around a braid relation. I might as well write this down as Si squared equals 1, Si Sj equals Sj Si if I is different than j plus or minus 1 mod k. And the same thing, Si plus 1, Sj, Si, sorry, equals Si plus 1. For the same, sorry, I is mod k. So I just added a generator by, I made this thing humongous because this group has order n factorial, this group is infinite. Okay, and just like I can look at this group as generated by permutations, there's a representation for this group. Okay, I'll show you quickly. Have you seen the affine symmetric group?
Did it come from braided group?
Yeah, sort of. We can look at it as braid group. But we can actually look at it as infinite permutations with some condition. So this is how it goes. I'm going to do S4, for example. So S4, okay? So I'm going to think of S4 really permutes 4 elements. S4 tilde permutes really long rows. 0, minus 1, minus 2, minus 3. Okay? And before, S1 does this, S2 did this, and S3 did this, permuting 3 and 4, and 2 and 3, and yeah? Now, in every window, S1 is going to do the same thing. So S1 permutes the 1 and 2, but also the 5 and 6, and the 9 and 10, and the minus 3 and the minus 2. Okay? And S2 does everything, you know what I mean, right? Well, what do you think? What do you think S0 does? The only thing that's left. So S0. No, it actually simpler than that. It flips two things among the wall, around the wall. So add this. Okay, and so this actually has some properties. The things in each wall always add up to n choose 2, which is 10. And everything in each wall, when you walk 4 steps, is 4 more than what it used to be. You know what I'm saying? Should I write it down? The things on the main wall add to n choose 2, which is 4 choose 2, which is 10. And this is always, if I walk to the element in the next chamber that is in the same position, it's always 4 plus, and then 4 plus, and then 4 plus, no matter how many of these relationships I use. So it's special words. You can't get any word like this, but everything you can get is in the affine symmetric group. Okay? Does that make sense? Okay, so just like in here, I can express every element as a product of these. I can do the same thing here, right? And I have a concept of reduced words, right? So reduced, for example, this is an element, okay? Of this, gives me some permutation, and I cannot express it using less than 3 generators. So it's a reduced word. Can somebody help me think of something that is not a reduced word? Yeah, S1, S3 one's pretty good because S1, actually I'll make a better one, S1 squared, because that's nothing, right? I can express it with 0 generators. Or even a more interesting one, S1, S2, S1, S2. Because this by braid relation is the same as S2, S1, S2, S2. And this is nothing with the identity, so this is 2 as 1. So this word is reduced, this word is not reduced. This word is not reduced, this one is reduced. Okay, so we have this concept of reduced words. And now, I'm going to show you something how some reduced words become k-Schurs. Okay? And so the way a reduced word becomes a k-Schur is by doing exactly this procedure. I'll give you an example. So now we switch to S3, which is generated by S0, S1, S2. And I'm going to come up with a random word. S0, S1, S2, S1, S0. So I say that this word can be made into a k-Schur in the obvious way. I take this letter and I add all the zeros. Okay? I take this letter and I add all the ones. I take this letter and I add all the twos. You see what I'm doing? I take the next one and I add all the possible ones. And I take the next one and I add all the possible zeros. Okay? So, k-Schurs and reduced words. Well, this is not a bijection because it's actually some reduced words are in bijection. And the bijection is this. Now, some of them can't. Can you give me a word that can't be turned into a core?
S2.
Exactly. S2 can be turned into a core because I can't just add the 2, right? So it has to end in 0. The word has to end in 0. Because if I don't end in 0, then I can't start creating my core. Do you think that's enough, that it has to end in 0? You don't think so, right? What if we have, like, I'll give you an example. S0, S1, S0. That's no good, right? Because I can add the 0 box. Then I add the 1 box. And then I can't add a 0. Why is that? Because by the braid relation, this is S1, S0, S1. And that's no good. So I need that every reduced word ends in 0. And that's enough. So every reduced word ends in 0, in S0. And that's enough. These are called Grassmannian words. I'm probably out of town, right? Yeah, I shouldn't. So is this clear? And so what we did is these graphs, each vertex corresponds to a Grassmannian word. But there's a lot more words. And so we extended this graph. Well, actually, this is from works from somewhere else. Lapointe, Lam, Mars, and Shimozono extended these graphs to all the words, not just Grassmannians, but all of them. And it's too much to draw them, but I printed. Tony has kindly printed some for me. And so this is the weak and the strong. Weak and strong. Weak and strong, and for you. That's how it looks if I were to take these two graphs and add all the other words in a way that is consistent. Okay? And now, with these new graphs, the big graphs, we can create symmetric functions in the exact same way as I did before. And they're called strong-Schur functions and weak-Schur functions. And we can prove, our paper basically proves that they're symmetric and that they belong to this ring that I mentioned before. And basically that's what our work was. And I think that's all.
So they belong to that space, or they?
Yeah. So here I define in the big graph that you have, I define strong. This UV is more general in many ways because it also has not just going all the way here, but you can start anywhere and end anywhere. Mm-hmm. And they're pretty important, like geometry. They also appear in some cohomology classes. And so it was a conjecture that they're symmetric and that they belong to HK. Sorry, I meant to say H. I meant to say symmetric functions. The ring generated by H1 to HK. Mm-hmm. Would prove that they belong to here. So they obviously belong to ring symmetric functions. And they're, for U and B Grassmannian, they're positive sum of k-Schur functions. So.
And is it a basis of Grassmannian or not?
It's not a basis because there's too many. Because for the Grassmannians, basically, Sk of lambda is a basis for this. So basically, there's a basis for each. A basis has the size of course, and we have more because we added a lot more vertices. So we don't have a basis. It's way too many. But they're positive in this basis, so they can be expressed as a positive sum of sums in this basis. So, thank you.